At this point, I want to talk about some corollaries to Cauchy's integral formula. And before we do that, I want to remind you about the mean value theorem for integrals. This is not something that gets talked about in most Calc 1 courses. So namely in Calc 1, people generally talk about the mean value theorem and Rolle's theorem and how they are equivalent statements and follow from one another. But the mean value theorem for integrals is a little bit different. Okay, it's basically the mean value theorem over specialized functions. So the mean value theorem for integrals says the following. If f is continuous, so here f, we're just thinking about the land of single variable functions over real values, right? So if f is continuous on some interval from a to b, then there exists a value c. So there exists a value c between a and b, so that the average value or the mean value of our function is equal to f of c. So remember that the mean value is 1 over b minus a, integral from a to b, f of t dt, and that's going to be equal to f of c. Now, that looks a whole lot like Cauchy's integral formula. If you think about it, right? You had the 1 over 2 pi I integral from a to b, but it's going to look even more like Cauchy's integral formula if you apply the definition of the integral. So namely, let's think about Cauchy's integral formula as, so let's go back to the land of complex analysis here. Cauchy's integral formula says that, so Cauchy's integral formula says that f of w, so under the right set of circumstances, f of w is 1 over 2 pi I, integral over gamma, f of z over z minus w dz. And so here, let's let gamma be w plus r e to the it. Here, little r, where t goes between 0 and 2 pi. So again, here I'm even being bad at notation, but I'm abusing notation by confusing gamma and its parameterization, gamma of t, but that should be clear. So gamma of t is w plus r e to the it. And let's think about what happens when we plug this in to f. So it turns out that this is going to be 1 over 2 pi I times the integral over gamma. Gamma is going to be parameterized from 0 to 2 pi. F of z, so z is going to be, so this is f of gamma, so this is just f of w plus r e to the it. There's not really anything that you can say nicely there. Divided by z minus w. So here again, we're going to plug in gamma for z. So this is going to be w plus r e to the it minus w times gamma prime. That's going to be r I e to the it dt. Now, what's going to happen is some stuff cancels, so namely the w's. R e to the it is going to cancel with r e to the it. This I here is going to cancel with that I here. And what we're going to end up with is this integral of 1 over 2 pi. So we integrate from 0 to 2 pi of f of w plus r e to the it dt. And that's going to be f of w. Okay, so this is what Cauchy's integral formula says when you actually apply the definition of the integral. Here. And now this looks even more like the mean value theorem for integrals, right? Because this integral from 0 to 2 pi is going to be, that's your 1 over 2 pi minus 0 times the integral of f. And that's going to be equal to f of w. Okay, and so that's kind of our first corollary to Cauchy's integral formula.